For
Okay.
sure.
All right. So here we are at my office hours on Friday for Chemistry 2330. What we're going to do is we're going to hit the highlights of Chapter 14, which are some of the functional derivatives of carboxylic acids. So as we talked about in chapters 12 and 13, we talked about the chemistry of the carbonyl and how when we had aldehydes and ketones, we had a certain chemistry, and by adding that electronegative oxygen hydrogen to it, we turned it into the carboxylic acid, and now it became different different chemistry altogether. So now we're going to look at all the different derivatives, and these are the highlights of chapter 14, specifically the different types of derivatives we have and how to convert them from one to the other, okay? So the first thing I'd like to go to is actually looking at the different functional groups we have. So we had the carboxylic acid. When we take that OH off and add a chlorine, we actually now make it more reactive, okay? So we have what we call an acid chloride, okay? When we have an acid chloride, this is the most reactive of the carboxylic acid derivatives, okay? Because we have chloride as a really good leaving group, it reacts with almost everything. It reacts with water, just in humidity and air, okay? The next most reactive is what we call the acid anhydride. You take two carboxylic acids, remove water, hence the anhydride, and then what you end up with is when you get attack at either one of those carbonyls, you have an acetate or carboxylic acid anion as a leaving group, which is also a good leaving group. Sorry, grab some coffee here. Okay, so that means that we have a chloride as a really good leaving group, an acetate ion as a pretty good leaving group. So those are the two most reactive species we have for carboxylic acid derivatives, okay? Now we move down to the two less reactive species. If we look at, for substitution reactions, the carboxylic acid would have a hydroxide as a leaving group. This is not a very good leaving group. So it's less reactive than the anhydride. It's about the same as the ester. Because when you have an ester and you're displacing something off of that carbonyl, you end up with a alkoxide anion as your leaving group, which is not a great leaving group, but we use the alkoxide for a lot of things, so we can actually displace it if we have something that's more basic than the alkoxide we're displacing it with, okay? And so that's why we can actually hit it with an amine, because that would be more basic, and produce the amide, which is the most stable of the carboxylic acid derivatives, other than the acetate ion itself. If we took a carboxylic acid, deprotonated it, that is the most stable. Nothing's going to happen to it other than it's going to act as a base, okay? So in all of these derivatives, we make them by basically reacting the carboxylic acid with something else and removing water, okay? In the case of the acid chloride, it could be HCl. In the acid anhydride, it's just water itself with another carboxylic acid. In the ester, it's the carboxylic acid and an alcohol. And in the amine, the amide, it's the amine and the carboxylic acid. So that's the first important thing, with different classes, and they have different reactivity. And as I alluded to before, the different reactivities have everything to do with the idea that the basicity of the leaving group makes it a poorer leaving group, meaning the basicity of the leaving group makes it more likely to displace the things that are above it. So in this case here, amide is our most stable functionality because the leaving group would be this amide amide anion, and that is the most basic of the set, followed by the alkoxide, the acetate, and then the chloride ion. So it's all about basicity, all about what would be the better nucleophile. Okay. So that being said, whenever we think about reactivity, the amide is the least reactive to substitution at that carbonyl because of the strength of that leaving group, okay? The fact that it's a really bad leaving group makes it the least reactive of the set. Because the chloride is the best leaving group of the set, it is the most reactive of the set, okay? All right, so that's in the introduction here. Now let's talk about interconversions of going from one to the other, okay? So you can always go from a more reactive carboxylic acid species to a less reactive carboxylic acid species. So if we take just each of those classes and react them with alcohols, we see this to be true, okay? We can take an acid chloride here. In this case here, an acid chloride reacted with an alcohol. It immediately does an acid-base reaction, producing HCl and creating an ester with our function as our functionality. Again, we can react an anhydride with that alcohol, and it does a similar reaction, creating an ester. However, because the leaving group is this acetate ion, on this case, or that carboxylic acid group, the proton from the alcohol ends up shifting to that acetate ion to generate one equivalent of carboxylic acid and one equivalent of ester, okay? So whenever you have an anhydride, you always get one equivalent of ester and one equivalent of the carboxylic acid. But again, the acetic anhydride, sorry, the acid anhydride is more reactive than the ester, therefore we convert it from the acid anhydride to the ester. Okay, so now we can actually get esters to react with other alcohols to exchange, okay? So while we're not increasing the stability or decreasing the stability of the product, we can actually use a catalyst to drive the reaction to that exchanged product, okay? Now, it happens spontaneously and is in equilibrium, okay? If you want to force it to one or the other, the best way to do is to drive off one of the alcohols. Either to remove the alcohol because it precipitates, it doesn't dissolve, or in the case of a small molecule like methanol here, we can just boil it out of the reaction. And so it's basically taking a stable carboxylic acid derivative ester and turning it into another one, but you're having a driving force. And so this exchange is possible, although you need to, have special conditions to make it happen. It's not spontaneous. Okay. So that being said, amides are less reactive than esters. Therefore, you cannot convert an amide to an ester because that would be going to a more reactive species than a less reactive species, and therefore you cannot do that. Okay. So we're going to see the same analogous behavior when we act amines with all the different functional acid groups, okay? So if we take an acid halide, it has to react with two equivalents of an amine because we're going to generate the salt with the acid, with the chloride. Therefore, we're generating some kind of acid from that. So part of the ammonia or part of the amine acts as a base and takes away the HCl. The other equivalent of the amine goes and it attaches itself to the carbonyl to make that stable amide compound, okay? So it'll also react with acid anhydrides because the acid anhydride is more reactive. In the case of the acid anhydride, we again have to use two equivalents of an amine because one equivalent is going to make our amide and the other equivalent is going to react with the carboxylic acid leaving group produced to create a salt, okay? So just like in the case of reacting with the acid halide, we have to have two equivalents of an amine. Because we're generating HCl, one of those equivalents of amine acts as a base to neutralize the acid given off, okay? So that's different than when we react an amine with an ester, okay? When we react an amine with an ester, we actually have a neutral species leave, okay? When the hydrogen is transferred from the amine to the alkoxide, we now have a neutral ester. That means we only need one equivalent of the amine to make that reaction happen because we don't need to have the excess amine as neutralizing the carboxylic acid salt, the carboxylic acid or the HCl, okay? So that's the key here is that we now only have to use one equivalent of amine to get to the more stable amide. And then of course the amide itself doesn't react with other amines, okay? You've already created the stable amine. If you want to convert it to a different amide, you have to do some other reaction on it, okay? So that brings us to this table here. So what we want to think about when we look at this table is that the higher you up on this, the y-axis here, the more reactive you are, okay? Which means we can take any acid chloride derivative and convert it to any of the other derivatives, okay? By just reacting the acid chloride with water, we can get to the carboxylic acid. By reacting it with a carboxylic acid, we can get to the anhydride. By reacting with an alcohol, we can get to the ester and amine. And likewise, we can make the anhydride into esters and amides and down to salts, but we can't go up. This is making it more reactive. We cannot do that directly. We have to convert it all the way down to the carboxylic acid and then convert it, okay? So again, the ester cannot be used to create the anhydride or the acid chloride, but it can be used to create amides. And again, the amides can't react with anything, but you can hydrolyze away the amine with strong base. What that'll give you is that'll give you the alkoxide anion, which then you can protonate. Once you have the carboxylic acid, you can then convert it to the higher. You can convert it to the acid chloride. You can actually also convert it to the anhydride using a catalytic system. Okay. Okay. For those who are just joining, I'm hitting the highlights of chapter 14, carboxylic acid derivatives. This video should already be posted on the internet. The remaining chapters of 15 and 16 will be posted today and this weekend. Okay, on our last section of chapter 14 here, we're looking at, we looked at this interconversion here, but besides just interconverting between the different functional groups, there's additional chemistry you can do. Just like aldehydes and ketones, we have oxidation and reduction reactions. So let's look at those oxidation and reduction reactions. The first thing we can do actually is we can also do, instead of just doing substitution reactions where we maintain the carbonyl group, we can react them just like we did ketones and react them with Grignard reagents, okay? Remember, in a Grignard reagent, the carbon of the Grignard reagent is a negative carbon right here. And so that negative carbon is going to attack our carbonyl carbon because of the partially positive side of the carbonyl carbon. And that's what's going to give us our addition reaction. Now, in the case of the Grignard reactions, we actually have to use 2 equivalents of the Grignard and we'll generate an alcohol. It doesn't like to stop halfway through. It'll give you a mixture of products if you try to. So you typically use 2 equivalents and then therefore you get it. If you have the ester of a formic acid, okay, you will generate a secondary alcohol because one will attack first to generate your primary alcohol. You'll regenerate your ketone, and then a second one will hit to create your secondary alcohol, okay? In the case of a regular ester where you have you're going to add 2 R groups onto it, which means you're going to generate a tertiary alcohol, okay? Note, this has to be with an ester. You cannot do it with a carboxylic acid because if you try to do it with a carboxylic acid, the Grignard reagent would pull the proton off the acid and quench the reaction, and it would stop. So it has to be the ester, okay? So, so the first step of the reaction is the attack by the carbon nucleophile, generating this tetrahedral intermediate, which then can have the electrons from the anion here of the oxygen kick down and give us our carbonyl compound again. And remember, our carbonyl compounds also will react with Grignard reagents. So that Grignard reagent will react, the second equivalent will react to give us our second substitution. And once we get our second substitution, we now have that oxygen anion, but it cannot convert down to an aldehyde again. I'm sorry, a ketone again. Therefore, it stops at this salt, and this salt then has to react with water and acid to generate your alcohol in the terminal step of the reaction, okay? So really, the idea is that one equivalent comes in, attacks, you reform the ketone, or reform the carbonyl, and then a second equivalent comes in and attacks the ketone again, okay? So that's why you have to use 2 equivalents, and why it doesn't stop halfway through, because one will displace the ester and then one will start to react with the ketone as well, and you have a mixture of products. Okay. So the next reaction we can do is just like with the carbonyl reactions, we can actually reduce down the carbonyl, okay? Now in the case of esters, what we end up doing is reducing an ester all the way down to a primary alcohol, okay? So the reason it's a primary alcohol is the alkoxide is one of the groups that leaves, and then we added 2 hydrogens across there, so we generate a primary alcohol from the system, plus one equivalent of the alcohol that was used to make the ester, okay? Now, the cool thing is that the other reagent we had that reduced aldehydes and ketones, which is the sodium borohydride, is not strong enough to reduce off this alkoxy group here of the ester, which means it still will reduce the aldehyde or the ketone, but it won't touch the ester. So we can selectively choose, do I want to react the ester? If I want to react the ester, it's going to react with the ester and the ketone. If I don't want to react the ester, I use sodium borohydride, and it'll only react with the ketone or the aldehyde. So this is the cool part of chemistry, is you get specificity. Choosing the reagent, you can choose one reaction over the other. Okay, so in the case of lithium and aluminum hydride, it'll also reduce down amides to amines. Now, if you had a primary amide, you will get a primary amine. If you had a secondary amide, you will get a secondary amine. If you had a tertiary amide, you will get a tertiary amine. So it does not remove carbon-nitrogen bonds. All it does is take the carbonyl all the way down to a CH2 group. That CH2 group will still stay bonded to your nitrogen. So that's a really nice thing to do, because it doesn't change the chemistry around the amine. And as we learned in amines, that one of the reactions we can do is it can act as a nucleophile, but it's really hard to stop at a primary amine or a secondary amine if you take an amine and react it with an alkyl halide. This way, if you make a secondary amide, you can make a secondary amine out of it. So it's a really subtle little trick that you can use as a chemist to get exactly the structure you want. All right, so that brings us to this slide here. And this slide here is all about, okay, adding to that inner conversion chart that we started before at the beginning of this slide, at this set of slides, and the idea that we can take our carboxylic acid or our carboxylic acid derivative, in this case, we're taking phenylacetic acid, and we can convert it to an acid chloride. We didn't show you how to make an acid anhydride out of it, but you can, okay? We can also convert it either directly to the ester using acid, or take the acid chloride and react it with an alcohol. We can also take it and convert it to an amide by converting it with the acid chloride or the ester. We can also do it with the acid anhydride, but that's not on this page. Or we can go all the way down to a primary alcohol or a primary amine by using our lithium aluminum hydride reagents. Notice the lithium aluminum hydride will also convert a carboxylic acid directly. And in the first case, instead of taking out an alkoxide, it's taking off a hydroxide. In this case, it's taking off an alkoxide to generate that primary alcohol. And in this case, we had a primary amide, so we're converting it to a primary amine. If we had a secondary amide, we'd get a secondary amine. If we had a tertiary amide, we'd get a tertiary. So that's the cool part about carboxylic acids, is it's really easy to start from a really easy to make, because you oxidize it to get to your carboxylic acid, and then you can do a lot of different derivatives all the way with very simple chemistry, lots of acid and base chemistry to convert it to different substrates. Okay, so that's what I think are the highlights of chapter 14. Okay, and then chapter 15, I want to say, is enolate chemistry. So when you look at the videos for enolate chemistry, again, we're looking at that carbonyl is our primary functional group, but instead of doing reactions on that carbonyl, we're actually using it as an electron withdrawing group to change the acidity of hydrogens that are one carbon over, or in that alpha position, that one carbon over. So when we talk about enolates, we're still talking about carbonyl chemistry, but we're using the carbonyl as a directing group, not actually doing reactions on the carbonyl itself. Okay? So does anybody have any questions about carboxylic acids, carboxylic acid derivatives that we can go over while we still have some time here? We have at least 10 minutes before I'll shut off this video and let it upload it to the internet. Anybody have any questions on aldehydes or ketones? Okay. On my office hours for the 22nd of April, I did the highlights of aldehydes and ketones also, but I can do that if anybody has any specific questions. Let me put on my chat real quick. I don't have any additional chats here. So, while I have a video going here, let me go ahead and do a little administration while somebody's typing their stuff into chat here. This week, we have to watch chapters 12 and 13, which is aldehydes and ketones and carboxylic acids. The homework for that is due on Friday. I double checked that. It's good. Your quiz 9 should be in Dropbox now. It's due at 5 p.m. today. Next week, you'll have chapter 14 and 15 homework due on Friday. I have that over here. So yeah, chapter 14 and 15 homework will be due May 1st, Friday, May 1st. And then chapter 16 homework will be due Monday, May 4th, okay? I had to squeeze it in before the last class day, which is May 5th. So we will have a quiz next week. It'll be quiz number 10, and then we'll be done with quizzes. And we should have enough time at the end of, on Friday of next week and Monday of next week and Wednesday of the following, Monday and Wednesday of the following week to do a review for our final. Our final will be comprehensive from chapters 1 through 16 in Poon and Brown. And so we will, and it will be multiple choice and administered on the day of that we are scheduled for finals. Okay, and the day we are scheduled for finals is, right now it's scheduled for May 8th. So our final will be administered on May 8th. A lot of my colleagues at Texas State, we want to make sure that we all administer our finals on the day we were currently scheduled for it so we don't have mismatch and overlap. And all finals will be administered online. None of them will be given in person on campus. Okay. So I will stop sharing here. And if nobody has any specific questions right now, I'm going to go ahead and stop recording, and then I'll upload this, the highlights of carboxylic acid derivatives to my YouTube channel.